Metal oxide semiconductor field effect transistor. In short, we call it as MOSFET. And the other name for this is IGFET, insulated gate field effect transistor. Insulated gate field effect transistor, or also metal insulator field effect transistor. Okay, and here this can be operated in two modes, and it is of two different types of channels. So we have total four devices in MOSFET. So first, enhancement mode MOSFET, P channel and N channel. Next, depletion mode MOSFET, P channel and N channel. Okay. So previously we discussed two, now four devices. Okay. No need to worry. We'll discuss one N channel enhancement, one N channel depletion. Okay, that will be very easy. So these are the circuit symbols of these four devices. Here, these two symbols are same, but the only thing is this substrate is connected to source. In general, substrate is connected to source. So that one shown here. So either you can use this one or this symbol or this symbol for the depletion mode MOSFET. So in depletion mode MOSFET, the channel is continuous. So the channel is continuous. That is, during the manufacturing process only, channel will be induced. Channel is depleted in the substrate. So that is why it is continuous channel. So we have continuous line shown in the symbol for the depletion MOSFET. For the depletion MOSFET, whether it may be N channel or maybe P channel. But coming to the enhancement mode MOSFET, this channel is induced depending on the applied voltage. During the manufacturing process, channel is not depleted. Channel is induced depending on the applied voltage. So that is why, as channel is not continuous in the case of enhancement mode MOSFET, we have shown that with broken line here. We have shown with broken line. Here you can observe this one. So continuous line is there means that is depletion MOSFET. Broken line is there means that is enhancement mode MOSFET. Okay, and always one thing you have to remember is for N channel, whether it may be JFET or maybe MOSFET, for N channel, the current flows inwards. Current flows inwards. So arrow mark is inwards, and for P channel, JFET or MOSFET, current is arrow mark direction is outwards. So this one you have to remember. And if it is JFET, the arrow mark is there on the gate terminal. Arrow mark is there on the gate terminal. But if it is there on MOSFET, the arrow mark is there on the body or substrate. Substrate or body. Okay. So in this way, you need to remember the symbols. Next, let us see the N-channel MOSFET. So first we will see enhancement mode. N-type enhancement mode MOSFET. So in this construction, first for N-type, for N-channel, P-type substrate will be taken. Whereas in case of N-channel JFET, the substrate taken was N-type material. But coming to the MOSFET, for N-channel MOSFET, the substrate taken is of P-type, opposite type. Okay, for JFET, substrate is same type of material as the channel. But in case of MOSFET, the substrate taken is of opposite material of the channel. Okay, so here this is N-channel, means the substrate taken is P-type substrate. On this P-type substrate, first silicon dioxide layer is grown, and wherever you require source and drain terminal, there it will be etched. So that means this portion, these portions, this layer will be removed. And then N-type impurities, heavily doped N-type impurities are diffused into these regions. Okay, these regions. And then metal contacts are made to these regions. Okay, now you can observe here, metal contacts are made at this N region, and that will be called as source terminal. And for this region, For this region, metal contact is made, and that is called as the drain terminal. And the metal which is deposited over this silicon dioxide in the region between the source and the drain, so that region, that terminal is called as the gate terminal. In the region between source and drain, uh, on top of this silicon dioxide layer, metal is deposited, so which is acting as a gate. That means for JFET, actually gate is of semiconductor material. So if it is n-channel JFET, then gate is of p type. If it is p channel JFET, then gate is of n type. But coming to this MOSFET, if it is of n channel MOSFET or p channel MOSFET enhancement or whatever may be, for MOSFET, gate is metal. Gate is metal, not semiconductor material. So these are p type and n type semiconductor materials, right, for JFET. But for MOSFET, gate is of metal. Gate is of metal. So this is the difference. And next, here the region between this source and drain. So below this oxide layer is used as a channel. It is used as a channel. Okay, let us see how this channel will be induced in this particular enhancement mode MOSFET. Now, I hope this is clear. So in the N-type enhancement mode MOSFET, first, again, let us see. First, for N channel, P-type substrate is taken, and then silicon dioxide layer is grown, and wherever you require source and drain, then there it will be etched. That means the silicon dioxide layer is removed, and then heavily doped N-type impurities are induced into this P-type substrate, which forms the source and drain regions, and then metal contacts are made on these two regions, which are called as source and drain, and metal contacts are also made to the substrate, that is body, and also on top of silicon dioxide layer, also metal contact is made between the source and drain region. So that terminal is called as the gate terminal. So in this way, we have four terminals actually. You can see source, gate, drain, and also the terminal, the metal contact made to this substrate is called as the body terminal or substrate terminal. So this is the construction of MOSFET, and the channel is not present in this case during this process, so we call it as enhancement mode. Channel is not present now, and it will be present depending on the applied voltage. Now let us see creation of a channel. So how the channel is induced in case of this enhancement mode MOSFET, let us see now. Now here at the gate terminal, we are applying positive voltage. So if we apply positive voltage, then what happens? Let us see. Okay, at the gate terminal, I am applying positive voltage. That means the positive terminal of the supply is connected to gate and negative is grounded. So some positive voltage is applied on gate metal. Now, so this is of metal, and this generally acts as a parallel plate capacitor. So this gate, and in between you have silicon dioxide. This silicon dioxide acts as a dielectric, and this metal plate, gate metal plate, and the region below this silicon dioxide between source and drain. So this region acts as one more parallel plate. So this acts as a channel. So the region between source and drain below this gate region is the channel region. Okay. Now now this, along with this gate metal and this channel region, this acts as a parallel plate capacitor. So internally between these plates, now we have the dielectric, and this gate and this width is very small, so that this is having more capacitive effect. So that this acts as a parallel plate capacitor. Now, when you apply positive voltage at the gate, now this region is actually P-type substrate. So P-type substrate means it has both majority and minority charge carriers. Majority charge carriers are holes and minority charge carriers are electrons. We have both majority and minority charge carriers here in each type of material, P-type and also N-type. Here majority charge carriers are holes and minority charge carriers are electrons. Now when you generally give positive voltage to the parallel plate, one of the parallel plate, then negative voltage will be induced in the other plate. So that this is indicating the polarity of this capacitor, right? So here also the same thing happens. When you apply positive voltage at the gate, this will attract negative charged particles. That means here you have both positively charged holes and negatively charged electrons. So these electrons are attracted towards this region. So negatively charged electrons are attracted towards this area. So in this way, now in this P-type substrate, on top you have a layer of these electrons, So this layer is called as a channel or inversion layer, this region. So actually it should have positive charges, but here all the negative charges are attracted towards here. They are accumulated near this region, near this gate region. So we call this area as a channel, and this layer of these electrons is called as inversion layer. Now, so if you go on increase this gate positive voltage, then a sufficient number of electrons are accumulated here so that the current will flow through the MOSFET. So the minimum voltage that you need applied at the gate terminal is called as the threshold voltage. So which will accumulate sufficient electrons here so that current will flow through this region, so that these negatively charged particles. So when we apply some voltage here, say negative terminal is connected to source and positive is connected to drain, then what will happen? This negative terminal will pushes the electrons in the source region to the channel. Here now we have this channel area. In this area also we have negative electrons. So the electron coming from this source will push this electron. So it will move forward. Similarly, this will move the other one forward. So that forward. So in this way, electrons from source will be traveling through this channel and to the drain, and from the drain they are attracted towards the positive terminal of the supply. So in this way, current will flow through the MOSFET. So current flows through the MOSFET from source to channel to drain to the supply. So from source, channel and drain. So this is the path for the current flow in the MOSFET. And this channel width depends on the gate voltage. So as more and more positive charge you apply, more and more negative charge will be accumulated in this region, so that more number of electrons will flow through this particular circuit, leading to higher current. So that means gate voltage is actually controlling the width of the channel, because more number of charges are accumulated means the width of the channel also increases. In this way, the voltage applied at the gate terminal is controlling the width of the channel. So as this Vg increases, applied voltage Vgs increases, then width of the channel also increases, which increases the current in the MOSFET. We have seen the construction of N-channel enhancement mode MOSFET, in which the substrate taken is of P-type material, and to which for both sides will N-type impurities are diffused, which forms the source and the drain, and the middle region over the silicon dioxide metal is deposited, which acts as the gate terminal. And in the case of N-channel enhancement mode MOSFET, so this voltage between gate and source is positive, and the voltage between drain and source is also positive. And there is no channel without applying any voltage at the gate. That means if gate voltage is 0, then no channel will be there. And channel is induced only when we apply positive voltage at the gate, then only channel is present. So which causes the current to flow in the N-channel enhancement mode MOSFET. Now, if you take N-channel depletion mode MOSFET, the construction will be similar, but during the manufacturing process itself, here N-type impurities are also deposited between these source and drain regions, so which provides the path for the charge carriers to move. So this path is now acting as a channel. So the channel is present even though without applying any voltage. That means whenever the applied voltage is 0, no voltage is applied at the gate terminal, then also channel is present. Channel is present. And if we apply positive voltage at the gate terminal, then when gate voltage is positive, then the width of the channel increases. Channel width increases as in the case of the enhancement mode MOSFET. But if the gate voltage is negative, then in that case, so the negative voltage applied at the gate will accumulate the positive charge below this silicon dioxide. Below this silicon dioxide, we have N-type material. In N-type material, we have electrons as the majority charge carriers and holes are the minority charge carriers. Now, as this negative charge which is applied at the gate will attract the positive charge which is there in this channel, these holes which are attracted towards the silicon dioxide layer. So these holes accumulated here will obstruct the flow of electrons. That means as you apply more and more negative voltage at the gate terminal, these more and more layer of holes will be formed near this region, so which reduces the actual width of the channel. So in this way, as the negative voltage is applied at the gate terminal, channel width will be decreased. As channel width will be decreased, current also decreases. Drain current decreases. As the channel width increases, current increases. So in both the cases here you can see as there is no channel, then current ID is 0. And now whenever channel is present, then current will be present depending on the applied voltage. If you go on increase the positive voltage, for depletion mode MOSFET, it actually operates in two modes. Depletion mode and also enhancement mode operation is also obtained by using the depletion mode MOSFET. So whenever the applied voltage is 0, then in that case also channel is present. And when the applied voltage is positive, then the channel width increases so that the current increases in the MOSFET, which acts as the enhancement mode. So this is when gate voltage is positive, then this is operating under enhancement mode. Depletion mode MOSFET operating under enhancement mode. And whenever you apply negative voltage at the gate, the width of the channel decreases and the drain current increases. So this is operating under depletion mode. Depletion mode. So in this way, depletion mode MOSFET can also be operated in enhancement and also in the depletion modes. Similarly, the case with the P-channel MOSFET. So again in P-channel MOSFET we have enhancement mode and depletion mode. Let us first see the P-channel enhancement mode. In P-channel enhancement mode, the construction is such that the material or base substrate taken is of N-type material, and for both sides we have P-type impurities which are diffused. And as it is enhancement mode MOSFET, no channel is present. Whenever gate voltage is 0, no channel is present, and channel is induced when you apply negative voltage at the gate. And when we apply negative voltage at the gate, then positive charges will be accumulated here near the silicon dioxide layer. So between the source and drain, because this is of N-type material which consists of both negatively charged particles and also positive, because these electrons are the majority carriers and holes are the minority carriers. These holes are attracted towards this silicon dioxide layer because on opposite side we have negative charge. So these positively charged particles are accumulated here, so that we have a layer of holes which acts as the channel between the source and the drain. So here the channel is of p-type, so that is why we call it as the p-channel MOSFET. And this channel is induced only when we apply negative voltage at the gate, so that is why we call it as enhancement mode. Channel is enhanced only depending on the applied voltage at the gate. And whenever negative voltage is applied, then channel is induced. Channel is enhanced. And similarly, in order to move the charge carriers from source to drain, we need to apply voltage between this drain and source terminals such that negative terminal of the supply is connected to the drain and positive terminal of the supply is connected to the source, so that this positive terminal of the supply will pushes the holes in the p-type source towards the channel, and from the channel these will be traveling towards the drain. From the drain they are attracted towards this negative terminal of the supply. So in this way current will flow in the p-channel enhancement mode MOSFET, and this direction is completely opposite to the direction of current flow as in the case of n-channel enhancement mode MOSFET. Now let us see this N-channel depletion mode MOSFET. In N-channel depletion mode MOSFET, the channel is induced or diffused during the manufacturing process. That is, already we have p-type channel which is present. Even though gate voltage is zero, now channel is present. And by controlling the voltage at the gate terminal, by changing the voltage at the gate terminal, we can control the width of the channel. So that is, when we apply gate voltage negative, then the width of the channel increases, channel width increases, which increases the current. So as you go on increase the negative voltage at the gate terminal, more and more positive charges will be accumulated here. So the width of the channel will be increased. So the current also increases. But when we apply positive voltage at the gate terminal, then opposite charge particles, that is electrons in this p-type channel, are attracted towards this silicon dioxide layer, so that you have a layer of electrons here, so which is obstructing the way for the holes which are moving from source to drain. So in this way the width of the channel decreases. Channel width decreases when you apply positive voltage at the gate terminal for p-channel depletion mode MOSFET. So as this gate voltage increases more and more positively, the drain current decreases. So whenever gate voltage is negative, it is acting under enhancement mode, and whenever gate voltage is positive, then it acts in the depletion mode. So in this way, depletion mode, p-channel MOSFET, depletion, n-channel depletion MOSFET will be operated in both enhancement and also the depletion modes. Now let us see the characteristics of MOSFET. Similar to the characteristics of JFET, MOSFET also exhibits three regions of operations. Those are cutoff region, ohmic region or linear region, and saturation region. In cutoff region, MOSFET is said to be off as there is no current flow. That is, the drain current is zero. So in this case, MOSFET acts as open switch, so that it is used in digital circuits. It is used as a switch in digital circuits. So in this cutoff region, it acts as open switch. And similarly, if you take the saturation region, then in saturation region, above the pinch of voltage, The drain current is almost constant, which is maximum. So therefore, it acts as closed switch. It acts as closed switch. So that is why it is used as a switch in digital circuits. So the MOSFET acts as either open switch or closed switch in cutoff and saturation region. So the application of MOSFET is that it is used as switch in digital circuits in these two modes. And the other mode is ohmic region or linear region. In this region, the drain current increases with the application of the drain to source voltage. That means if you go on increase VDS, drain current increases. It is depending on linearly with the applied voltage. So that is why this is also called as a linear region. And in this region, MOSFETs are acts as amplifiers. So these are the characteristics of N-channel enhancement mode MOSFET. So for N-channel enhancement mode MOSFET, gate to source voltage is positive and drain to source voltage is also positive. So both are positive. Now let us see the output characteristics first, that is figure B. Now as you go on increase this voltage between drain and source, that is as you go on increase the applied voltage starting from 0, then the current in the MOSFET increases. The current in the MOSFET increases. Say at a particular voltage, gate voltage called as VGS1. At VGS1 initially as VDS increases, current ID increases, and at a certain voltage called as pinch off voltage, say this is pinch off voltage, the current becomes maximum and after that it remains constant. So if you go on increase VGS, that is as VGS is increased from VGS1 to VGS2, then the width of the channel increases, then more and more electrons will flow from source to drain. So therefore the current also increases. So current also increases. As VGS increases, ID increases. So therefore you can see the curves. So these curves are shifted upwards as you go on increase VGS. So VGS1, VGS4 is greater than VGS3 and again this is greater than VGS2 which is greater than VGS1. So in this way as you go on increase the VGS, drain current IDS increases. And in this we can observe the three regions of operation. The region below this locus is ohmic region. So in which as you go on increase the VDS, drain current also increases. And the region after this VP in which drain current is constant, that is IDS is constant, is called as the saturation region. And the region below this VGS1 where VGS is 0, the applied voltage at the gate is 0, then there is no current flow in the MOSFET. So in this region, this acts as the off switch. So this is the cutoff region, this is the ohmic region, and this is the saturation region. And let us see the transfer characteristics. Now transfer characteristics are drawn for constant drain to source voltage, that is VDS. These are drawn for constant VDS and plotted between VGS and IDS. So plotted between VGS and IDS. As you go on increase VGS positively, here gate voltage is positive. So as you go on increase VGS positively, the width of the channel increases. Therefore, the current flowing through the MOSFET also increases. And so a minimum voltage required so that current can flow through the MOSFET. So that voltage is called as the threshold voltage. So at threshold voltage only current starts flowing through the MOSFET. And after VT, if you go on increase VGS, IDS also increases. Then the characteristics of P-channel enhancement mode MOSFET. For P-channel enhancement mode MOSFET, gate voltage is negative and drain to source voltage is also negative. So these characteristics are similar to the N-channel enhancement mode MOSFET, but with the polarities of VDS and VGS will be opposite. So that is, so as VDS is negative, now you can see this is a negative x-axis, and similarly the current is opposite to the N-channel MOSFET. So therefore, current is also taken on negative axis. So in this way, these characteristics are drawn in the third quadrant. In this case, again, as VGS increases, that means VGS increases negatively. That means as the magnitude of VGS increases negatively, then drain current also increases, because this increases the width of the channel. As width of the channel increases, current also increases. Similarly, the case with the transfer characteristics, as you go on increase VGS negatively, the current also increases. Now let us see the N-channel depletion mode MOSFET. In N-channel depletion mode MOSFET, gate voltage applied may be either positive or negative. So if it is positive, then it acts under enhancement mode, and if it is negative, then it acts under depletion mode. Now let us see the characteristics. Now if even though the applied gate voltage is zero, a minimum current flows. That depends on the applied voltage between drain and source. So as we go on increase the drain to source voltage, even though VGS is zero, now current will be present. Now if you go on increase VGS positively, that means the width of the channel increases here, therefore drain current also increases. But if you go on decrease VGS, that is negatively, then in that case current becomes very less and it becomes zero. So this will be more clear if you see the transfer characteristics. In transfer characteristics, now you can see even though VGS is zero, a finite current flows that depends on the VDS. Say this is plus 1 milliampere. Now, as you go on increase this VGS negatively, then here abstraction will be there. So therefore, the width of the channel will be decreased. So the drain current also decreases. So that means as you go on increase VGS negatively, then drain current decreases, and finally it becomes zero at a particular voltage called as the threshold voltage. And if you go on increase VGS positively, the curve is similar to the enhancement mode MOSFET. That is, as VDS increases, drain current also increases. In P-channel depletion mode MOSFET, the characteristics are similar to the enhancement mode MOSFET. As you go on increase the positive voltage, yes, you know that you gate voltage may be positive or negative. If it is positive, then it is depletion mode. If it is negative, then it is enhancement mode for the P-channel MOSFET. So whenever channel is present without applying any gate voltage, then in that case also a finite current flows. Say this is minus 1 milliampere, because this is opposite to the case of N-channel MOSFET. Next, as you go on increase VGS positively, then this is depletion MOSFET. That means the abstraction layer width increases. As a result, width of the channel decreases, which decreases the current. So the current decreases as you go on increase VGS positively. So therefore, as VGS goes positively during the positive x-axis, now you can observe drain current decreases and it becomes zero at the threshold voltage. Now, if you go on increase VGS negatively, then as you go on increase VGS negatively, drain current increases, because the width of the channel increases, the gate, therefore the drain current also increases. So in this way, you once relate the characteristics of all of these 4 types of MOSFETs. Thank you.